Hey, do you want to derive a gauge field that'll give a Lagrangian local SU3 symmetry? Well, if so, then I've got some good news for you, because that's what this video is all about. In part 1 of this video series, we talked about quarks, and we came up with this idea of a color triplet field, as well as a Dirac Lagrangian, which factors in the 3 different colors. And then we had this crazy idea, what if we took it as a first principle that we should be able to mess up our wave function with an arbitrary local SU3 transformation and have it not change anything observable about the laws of physics? And then in part 2, we learned some group theory that gave us the vocabulary and some of the conceptual tools that we'll need to derive our gauge field. And so now, in part 3, our objective is to derive a gauge field which is going to equip our Lagrangian for our color triplet field with local SU3 symmetry, so that as we hop from one gauge to another, and psi gets all messed up by our local SU3 transformation, we're going to bring in a gauge field that's going to come in and clean up that mess by transforming in a way which allows our Lagrangian to stay the same under every possible local SU3 transformation. All right, so we have this Dirac Lagrangian for a quark color triplet field, and as we've seen, if we apply a local SU3 transformation to psi, it appears to really mess things up. And so we strongly suspect that the laws of physics given by the Dirac Lagrangian should not naturally have local SU3 symmetry. We suspect that we have to add something to our model of physics to equip it with local SU3 symmetry. But in order to know what to add to fix the problem, we have to understand the nature of the problem. And so we want to analyze the Lagrangian carefully and confirm whether or not it does naturally have local SU3 symmetry, and if not, in what way does it fail to have the symmetry? Because that'll give us a clue about what we have to do in order to give our Lagrangian local SU3 symmetry. Okay, so in order to answer the question, we're going to imagine psi transforming under a local SU3 transformation. So psi becomes psi prime, which is given by U times psi, where U is a field of SU3 matrices which varies arbitrarily throughout spacetime. Okay, so under that transformation, psi becomes psi prime, which is U psi, and psi bar, that is the Dirac adjoint of psi, becomes psi bar prime, which is psi bar right multiplied by the transpose conjugate of U. You can prove that if you want, just by taking the Dirac adjoint of U psi. Okay, so now let's investigate the quantity delta L, which is defined as our transformed Lagrangian minus the original Lagrangian, so L prime minus L. And if delta L equals 0, then there is no change to the Lagrangian under a local SU3 transformation, and it naturally has the symmetry that we're looking for. But if delta L is non-zero, then our Lagrangian does not have local SU3 symmetry. So we can evaluate this by writing out the transformed Lagrangian minus the original Lagrangian. Notice that in the transformed Lagrangian, all we've done is we've replaced psi with U psi, and we've replaced psi bar with psi bar U dagger. Now, if we look at the expression shown here, we notice that on the mass term, there's this product of U dagger and U. But we know that U is an SU3 matrix, and so U dagger U equals I, right? I mean, that's one of the defining properties of an SU3 matrix. And so that term just vanishes away because we're just multiplying by 1. But then, once that term cancels out, you recognize that the mass term in the middle of the equation is exactly the same as the mass term on the right of the equation. In both cases, you have m times psi bar psi. And m is a scalar, so that commutes, so we can pull that out to the front. And so those two mass terms are going to cancel each other out. Okay, so things are beginning to simplify. And now, if we look at that derivative term, partial mu acting on U psi, we can use the product rule to go ahead and expand that out. So partial mu acting on U psi is equal to partial mu acting on U times psi, plus U times partial mu acting on psi. And then we'll go ahead and clean up and bring down the expression involving the I and the psi bar and the gamma mu partial mu psi. But now if you look at the two terms I've underlined here, on the left, you have this u partial mu psi, which is being left multiplied by I psi bar u dagger gamma mu, and the u dagger and the u are going to cancel out to I, and so when you evaluate that term on the left, you recognize that you end up with I psi bar gamma mu partial mu psi, which is the same term as on the right. And so those things are going to cancel out. And so now we can clean this up as psi bar I gamma mu u dagger partial mu psi. So evidently, that is how the Dirac Lagrangian changes under a local SU3 transformation. If you look at the form of this expression, you see that it involves things that are generally non-zero, because the matrix field U varies in space and time, so it's generally non-zero, and its derivative is generally non-zero as well. Also non-zero is going to be our wave function psi, as well as the imaginary unit I, and the gamma matrices gamma mu. So all of this here is generally going to be a non-zero quantity, and that means that no, the Dirac Lagrangian does not have local SU3 symmetry, because it changes under a local SU3 transformation. And so this is why, if we insist that our Lagrangian must have local SU3 symmetry, then we're going to have to modify our Lagrangian in a way that will necessarily give rise to a new interaction, and that is the strong nuclear force. So that's what I mean by local SU3 symmetry is like a magic bean that when you plant it, it bursts forth magnificently into the strong force, because if we take it as a constraint, as a first principle, as like this miracle that we're taking on faith, and then we say, okay, we're going to modify our model of physics in whatever way we have to satisfy this magical principle, then what you end up with is necessarily quantum chromodynamics. So now the question becomes, how can we modify our Lagrangian so that it remains the same before and after a local SU3 transformation? In other words, how can we give our Lagrangian local SU3 symmetry? Well, we saw that when we hop from one gauge to another, our Lagrangian changes by this amount delta L equals psi bar I gamma mu u dagger partial mu u psi, and when you look at it, everything here is generally non-zero, and that actually does make sense when you think about the fact that a local SU3 transformation is going to make all kinds of a mess in our wave function, because we're changing what we mean by color at different amounts and different points of space and time, and so there's going to be all kinds of gradients and all that sort of thing. And the energy pertaining to that mess is encoded in this non-zero delta L term. Now, in order to answer the question of how can we make this mess go away, let's think back to electromagnetism and see what we did there. Because if the strong force and electromagnetism are both gauge theories, then in principle, we can derive QCD in the same way that we derived electromagnetism, just with SU3 instead of U1, right? So we're going to leverage our experience with electromagnetism to guide us forwards as we figure out a way to give our Lagrangian local SU3 symmetry. Well, in the electromagnetism video, we derived the Lagrangian of quantum electrodynamics, which consists of the Dirac Lagrangian, which has to do with the wave function of a free spin 1/2 particle, but then that doesn't naturally have local U1 symmetry, so in order to give it local U1 symmetry, we defined a gauge field A mu and brought in this interaction term to clean up the mess. So now this pink term, the Dirac Lagrangian, and this yellow interaction term, together those two terms do have local U1 symmetry, because if you apply a local U1 transformation and analyze just those two terms in the Lagrangian, you'll see that while each one of those changes, together the result is the same. It's like a hand in a glove. And then in addition to that, we also have to give our gauge field A mu, that is the photon field, a life of its own, which is encoded in the photon field's contribution to the Lagrangian. Now the Lagrangian term pertaining purely to the photon field is whatever it can be without violating local U1 symmetry. And as we saw, if you're trying to think of what is an object that we can make purely out of the photon field that doesn't violate local U1 symmetry, Well, there's 6 ways to do that, and those 6 ways comprise the field strength tensor. And then if you want a Lorentz invariant scalar quantity based on that field strength tensor, you end up getting F mu nu, F mu nu. Anyway, we covered all that in the last video, so I'm not going to go over it again here. Oh, one more comment I'll say on this equation is in the last video, we used Gaussian units, so we had factors of h bar and c, and on the photon term, we had a 1/16 pi. But now I'm showing the equation with natural units to be simpler and consistent with this video series. So the h bars and the c's, those go away, and the 1/16 pi becomes a 1/4, because conventionally there's an extra factor of 4 pi in Gaussian units that we don't have to worry about in natural units. But anyway, I want to focus purely on the first 2 terms of the Lagrangian, the Dirac term and the interaction term. Now the thing to recognize about those terms, as I said earlier, is that those together already have local U1 symmetry. And so you can think about the interaction term in the Lagrangian as cleaning up the mess that would otherwise be present in the Dirac term of the Lagrangian under a local U1 transformation. But now if we want to, there's also another way to look at it, which is to define this concept of a gauge covariant derivative. We can define that as d mu equals partial mu plus iq a mu, where I is the imaginary unit, q is the coupling constant, in this case the electric charge, and a mu is the gauge field. And one of the reasons it's helpful to think in terms of the gauge covariant derivative is that it lets us write both the Dirac Lagrangian and the interaction term in one simple modified Dirac Lagrangian. You see, because we can absorb those 2 terms together into an expression that looks exactly like the Dirac Lagrangian, but with the partial derivative replaced with the gauge covariant derivative. And you can prove that by taking the right-hand side of this equation and substituting in, for d mu, partial mu plus iq a mu. Now the reason this concept of a gauge covariant derivative works is because of the way the gauge field a mu transforms under local U1 transformations. A mu is going to pick up a term proportional to the derivative of our U1 transformation phase field theta. And so because the behavior of a mu under gauge transformations is so closely related to the derivative of our gauge transformation, what the gauge field effectively allows us to do is redefine what we mean by the derivative from one gauge to another. Now this concept of the gauge covariant derivative, it's not a fundamental concept so much as a pragmatic concept. Often when gauge theory is taught, the gauge covariant derivative is listed as one of the primary fundamental ingredients, but that's not necessary. Well, there are ways of approaching the subject matter where you can put more emphasis on the gauge covariant derivative if you want to, but I think the subject matter actually makes a lot more sense if you take a different approach where you have your matter field and you have your gauge field, and then the gauge covariant derivative is just a pragmatic way of thinking about the interplay between the matter field and the gauge field vis-a-vis how the concept of a derivative changes from one gauge to another. But in any case, one of the defining attributes of the gauge covariant derivative is that it transforms in a very simple way from one gauge to another. Specifically, when psi becomes e to the I theta times psi under a U1 transformation, the gauge covariant derivative of psi becomes e to the I theta times the gauge covariant derivative of psi. And this contrasts with the usual notion of a derivative, which is very heavily messed up by a local U1 transformation that brings in all kinds of gradients and derivatives and things. You can't have an objective notion of the derivative of psi that exists coherently across different gauges, given that we're able to mess it up so much with a local U1 transformation. But we can have this concept of the gauge covariant derivative, which stays basically the same across all gauges, except for the fact that it has a phase factor which rotates in accordance with our local U1 transformation. And so the gauge covariant derivative is the closest thing we can get to this concept of a derivative that has an actual objective meaning across all possible gauges. And that's one of the main reasons why it's such a useful concept. And if you saw my video on superconductivity and the Higgs field, in which we used the notion of the gauge covariant derivative extensively to explore the Anderson-Higgs mechanism in a superconductor, and then also the Higgs mechanism in the Higgs field, then you'll see how powerful of a concept the gauge covariant derivative is. But today, we're not interested in applying the gauge covariant derivative, but rather, we're going to use this as a guiding principle that's going to help us find the kind of gauge field that we need in order to come up with a modified Lagrangian that contains an interaction term which does have local SU3 symmetry. So one way to think about it is like this. We have a Lagrangian that gets messed up under local SU3 transformations, and there's going to be a specific kind of gauge field which transforms in a specific kind of way that gives that Lagrangian local SU3 symmetry. And we don't have any choice in what that gauge field has to be. It has to be what it has to be. So this is sort of like looking for a needle in a haystack. When you think about all possible fields and all possible transformation rules, we want to find one in particular that fits and that cancels out the mess that would otherwise be created by a local SU3 transformation. And so in the analogy of we're looking for a needle in a haystack, we're going to use the concept of a gauge covariant derivative as like a metal detector that's going to help us hone in on the right answer, and then we're going to check that answer. And so basically, we're using our experience with electromagnetism to kind of hack into quantum chromodynamics because we can assume that there's going to be a structural similarity between quantum chromodynamics and quantum electrodynamics, and we're going to leverage that similarity to help us construct QCD in an analogous way to how we constructed quantum electrodynamics. And the way we're going to go about this is we're literally just going to copy and paste exactly what we did for electromagnetism, but we're going to make the bare minimum amount of changes that we have to make in order for this to apply to local SU3 symmetry. And those changes are as follows. Instead of using Q for the coupling constant, we'll use a lowercase g. Now fundamentally that plays exactly the same role as Q. We're just calling it something else so we don't get it mixed up with Q. So that'll be the coupling constant for quantum chromodynamics. And then, instead of using a mu for the gauge field, we're going to call it g mu. And again, g mu is basically the same thing as a mu. We know it's going to have to be a 4-vector field. The reason being, our local SU3 transformation is going to be able to make a mess across all 3 dimensions of space and the 1 dimension of time. So we can create a 4-vector of a mess, and therefore we're going to need a 4-vector of a gauge field to come in and clean it up. However, the 4 spacetime components of g mu are not necessarily going to be real numbers, like they are for the photon field. In fact, we should expect the spacetime components of our gauge field g mu to be 3x3 matrices, because of the fact that psi is a triplet. We'll get into that in more detail in just a moment. Oh, and then the other thing we have to do is instead of a U1 transformation e to the I theta, we have an SU3 transformation given by a matrix field U. So U is an SU3 matrix field that varies in space and time. Now, if we look at the equations that are in this box here, we have the definition of a gauge covariant derivative, which involves the partial derivative and a gauge field, and we know that from one gauge to another, we want our gauge covariant derivative to transform in a gauge covariant way, that is simply picking up a factor of u on the left as psi picks up a factor of u on the left. Well, that requirement actually imposes a constraint on g mu that tells us how our gauge field g mu has to transform from one gauge to another. So, implicitly, in what we've written here, we already have the properties of the gauge field that we're looking for. And now all we have to do is unpack what exactly those properties are, and then write out a Lagrangian with a Dirac Lagrangian and an interaction term, and then check that Lagrangian for local SU3 symmetry, and then we'll have demonstrated that yes, indeed, we have found the kind of gauge field that we're looking for, and that equips our Lagrangian with local SU3 symmetry. All right, let's see if we can derive the properties of the gauge field from our proposed definition of the covariant derivative. So let's review what we currently know about an SU3 gauge transformation. So suppose we're hopping from one gauge to another. Well, if we start off with some quark color triplet field in the old gauge, call that psi, then in the new gauge, psi becomes psi prime, which is simply equal to u times psi, where u is an SU3 matrix field which varies in space and time. And then we also have this notion of a gauge covariant derivative, where by definition, in the old gauge, that's going to be d mu acting on psi, and in the new gauge, we want that to transform so that d mu prime acting on psi prime equals u d mu psi. Now remember, that's an educated guess, based on our familiarity with the gauge covariant derivative from electromagnetism. We're using this educated guess as a way of trying to discover a gauge field that'll work for us for QCD, and that'll give our Lagrangian local SU3 symmetry. But we don't want to have to take it on as another first principle that this gauge covariant derivative thing should work. So remember, what we're going to do once we find the gauge field based on this covariant derivative is we're then going to drop the concept of the gauge covariant derivative and see if psi and g mu on their own interact in a way which gives our model local SU3 symmetry. So the gauge covariant derivative is a helpful tool for helping us figure things out, but it's not something that we have to take on faith forever. It's just an educated guess as part of the problem-solving process. Alright, so the gauge field. In the old gauge, we'll call it g mu. This will be some kind of a 4-vector field, although its components are presumably going to be matrix-valued. So now the question becomes, when we hop into a new gauge, and g mu becomes g mu prime, the gauge field in the new gauge, what should that be? Like, what is the equation in terms of the old gauge field and our matrix field u? How do we figure out what the gauge field is in the new gauge? Well, the idea is that it's whatever it has to be in order for the gauge covariant derivative to work. You see, because g mu appears in the definition of the gauge covariant derivative. And we have this educated guess about how the gauge covariant derivative should transform. So the gauge transformation rule for g mu is already implicit in those two equations, and now it's just a matter of algebra to work out the equation for g mu prime in terms of g mu. So for starters, what we're going to do is we're going to write d prime mu acting on psi prime as the definition of the gauge covariant derivative in the new gauge, that is partial mu plus ig g prime mu, acting on the triplet field psi in the new gauge, which is given by u times psi. And according to our educated guess, that should be equal to u times d mu acting on psi. So the equation we've written here is just the gauge covariant derivative transformation rule, but we've written out explicitly the definition of d mu as well as psi prime. Now in this equation, you'll recognize that there's a g mu prime and a g mu, so that's perfect. All we have to do is solve for g mu prime. Well, first, let's evaluate partial mu acting on u psi. We can use a product rule to calculate that. So partial mu acting on u psi is equal to partial mu of u times psi plus u times partial mu of psi. And next up, we have that term ig g mu prime times u psi. We can just go ahead and write that out as a product, like so. And then if we look at the derivative term, we have u partial mu acting on psi. And once again, we have another product, which we can write as ig u g mu psi. Now at this point, recognize that on both sides of the equation, we have this term u partial mu psi. So we can go ahead and cancel that out. And if we look at what's left over, notice that all of these terms have a factor of psi. So in order for this equation to hold true in general, for any psi, it has to be true even without the psi. So what we're doing here is essentially like dividing out by psi, although it's not exactly a division. It's more a recognition of the fact that in order for the matrix expressions on the left side of the equation to have the same effect as the matrix on the right side of the equation when acting on psi, then the left side and the right side matrices themselves have to be equal. But at the end of the day, we're basically canceling out a factor of psi. So now let's scoot some things around and write the equation like so. We'll bring the g prime term on over to the left. We'll bring the g mu term to the right. And we'll also bring that derivative of the matrix field term to the right. Notice that we've also divided out a factor of ig. And here you have to be super careful not to make a sign error. So what ends up happening is you move the derivative term over to the right side, and it should pick up a minus sign. But then you divide by ig, And that's the same as multiplying by negative I over g. So the minus sign times the negative I over g actually gives you a positive I over g. And now we are so close to having an equation that gives us g mu prime in terms of g mu and our matrix field. And all we have to do now to solve for g mu prime is to multiply everything by the transpose conjugate of u. Because on the left side of the equation, we'll end up with g mu prime times u dagger. But u is an SU3 matrix, so u dagger u equals I, and likewise u dagger equals I. So on the left side of the equation, when we multiply by u dagger, we end up getting g mu prime all on its own. And then on the right side of the equation, everything just picks up a factor of u dagger on the right. And there we have it. That is an equation for the gauge field in the new gauge, in terms of the gauge field in the old gauge, and the transformation matrix field U. So evidently, this is our gauge transformation rule. And now I want to reiterate, we haven't yet demonstrated that this is the case. This is simply a logical implication of our educated guess about the nature of the gauge covariant derivative. So we still have some epistemic debt that we have to pay off. That is, having derived this transformation rule, we still have to confirm that it is correct, that this does give us a gauge field which is able to equip our model with local SU3 symmetry. Now, of course, I'm not leading you down the wrong path here, okay? This is correct, and we will demonstrate that. But, we have to keep in mind what are the things that we have to do in order for this to be a really rigorous derivation, okay? So what kind of a field is G mu anyway? Well, one thing we can see right away is that G mu is a 3x3 matrix. Because we're adding this term, the derivative of u times u dagger, that's a 3x3 matrix right there. So what you want to imagine for G mu is it's sort of like the electromagnetic 4 potential A mu, but whereas that has scalar components, right, voltage and the 3 scalar components of the magnetic vector potential, this G mu is going to have 4 3x3 matrix valued components. And as you might have guessed, those components are actually going to live in SU3. We'll demonstrate that later on, but I just bring that up as a bit of foreshadowing. So let's take a closer look at what exactly this gauge transformation rule is telling us about the way the gauge field transforms from one gauge to another. Well, here's a good way to think about it. So when you hop from one gauge to another, what happens is that the gauge field is going to reorient itself in color space. And it's also going to pick up a derivative term which compensates for the mess that our local SU3 transformation would otherwise create. So when we're doing a local SU3 transformation, we're making all kinds of space-time gradients and things. It's very floppy, it's very scrunchy, the mess that we can make. And the derivative term comes in to clean that up. And that's very similar to what we saw for electromagnetism. In fact, if you set u equals e to the I theta, you'll find that this derivative term is actually exactly the same thing we saw when deriving the gauge transformation rule for the photon field. But there's something interesting about SU3 transformations that we didn't see when dealing with the U1 transformations of electromagnetism. And that is, even for a global SU3 transformation, where psi prime is just u psi and u is a constant SU3 matrix, so that the derivative of u equals 0 across all spacetime dimensions, then the gauge field is still going to transform, as shown here. The gauge field in the new gauge is going to be the gauge field in the old gauge inside a u dagger sandwich. And that's something called an adjoint transformation. So, we have this SU3 transformation matrix U, and when we slap that matrix U onto our quark color triplet field psi, transforming it into psi prime in the new gauge, that's called the fundamental transformation. Right? Like that's fundamentally how the transformation matrix is used. But apparently our gauge field is going to reorient itself in a different kind of a way. And as we'll see later on, that's because the components of the gauge field live in SU3, the Lie algebra of SU3. And so the way to think about the adjoint transformation is even if we're doing a global SU3 transformation, so we're basically redefining our coordinate system in color space, well, our gauge field has to reorient itself relative to that redefinition of our coordinate system in color space. Now, this is not something that we see when dealing with electromagnetism, although technically it is there implicitly. if you set u equals e to the I theta, being a u1 transformation of electromagnetism, then you find that this u dagger sandwich simply becomes e to the I theta times e to the negative I theta, which equals 1. And so technically, even in electromagnetism, the gauge field does undergo this kind of adjoint transformation, but it's totally trivial. The adjoint transformation is really not a transformation at all when you're dealing with electromagnetism. And that's because of the abelian nature of the U1 gauge group. Alright, so to summarize, we found what seems to be a plausible candidate for the gauge field, and we see that necessarily, under an SU3 transformation, the gauge field has to reorient itself in color space, and also pick up a derivative term that's going to clean up the mess pertaining to the spacetime derivatives of our transformation matrix field. Now this conclusion follows inevitably from our educated guess about the definition of the covariant derivative and the way it has to transform when hopping from one gauge to another. But we need to check our guess. And so the way to check it is to say, if we take our Lagrangian and we replace the partial derivative with the covariant derivative, then is that Lagrangian going to remain unchanged when we apply a local SU3 transformation? If so, then we'll have a Lagrangian that has local SU3 symmetry. And that's what we're looking for. Now, better yet, we can ask the same question, but without any reference whatsoever to the gauge covariant derivative. Because we can substitute into the Lagrangian the definition of the gauge covariant derivative, and then we arrive at a Lagrangian in which we're back to the regular old partial derivative, as well as an interaction term between psi and our gauge field g mu. Now that's exactly the same Lagrangian we've just written with the covariant derivative, but notice now that the d mu melts away, and so we can ask the same question while thinking purely in terms of the matter field psi and the gauge field g mu. So you see what we're doing is we're saying, okay, we used the covariant derivative in order to derive a plausible definition of the gauge field, but now we're going to test if this gauge field is indeed able to give our Lagrangian local SU3 symmetry. And we can ask that question in a way which doesn't invoke the gauge covariant derivative at all. So if we demonstrate that, then we're no longer reliant on any assumption about the gauge covariant derivative. And so now, if we'd like to, we can actually go ahead and discard the concept of d mu entirely, or we can keep it as a useful tool, and it is a useful tool, but it's not philosophically necessary. Okay, so let's demonstrate that our Lagrangian is unaffected by local SU3 transformations. So as we hop from one gauge to another, psi becomes psi prime, which is u psi. The Dirac adjoint of psi prime is going to be the Dirac adjoint of psi times u dagger. And our gauge field g mu is going to become g mu prime, which is an adjoint transformation acting on g mu. That's that reorientation in color space, given by the u dagger sandwich, as well as the addition of a derivative term that cleans up the mess pertaining to the spacetime gradients of our transformation matrix field U. Alright, so supposing we undergo an SU3 gauge transformation, let's go ahead and evaluate our Lagrangian in the new gauge. To do that, let's take the first term that involves the quark color triplet field psi, and we're going to replace psi with the transformed u times psi, as well as psi bar with the transformed psi bar u dagger. And likewise, if we look at the second term, we're going to make the same substitutions for psi and psi bar, and then we're going to replace the gauge field g mu with g mu prime, which is given by the transformation rule for g mu. And now all we have to do is evaluate this Lagrangian and see if it equals the Lagrangian that we started out with. So to do that, the first thing we'll do is we'll let the partial derivative act on u psi, and we'll go ahead and use the product rule. So partial mu acting on u psi equals partial mu acting on u times psi plus u times partial mu psi. Next up, we'll bring down the mass term, which should be psi bar u dagger m u psi, but because u is an SU3 matrix, we know that u dagger u equals I. And because m, the mass, is a scalar, we can scoot the u right up next to the u dagger and let those terms annihilate, so that we end up with the minus psi bar m psi. And similarly, if we go ahead and look at the terms highlighted here, you can see that you have two instances of u dagger and u multiplying to become I and dropping out of the equation. So we end up with an interaction term that looks exactly like what we started with in the original gauge. And then similarly, if we go ahead and bring down all this derivative stuff, it simplifies a little bit, and we get the expression shown here. Now, if you take a close look at the two terms I've underlined here, you'll see that they exactly cancel each other out. So that's good. That's a really good sign that we're on the right track. All right, so now if we gather up everything that doesn't cancel out and go ahead and write it like so. But wait a minute, look at what we have here. This is exactly the same Lagrangian we started out with. There's no difference whatsoever. And so yes, the Lagrangian is the same as before. So what have we done here? Well, we found a Lagrangian that involves our quark triplet field psi, as well as a gauge field g mu. The properties of the gauge field came from an educated guess about the nature of the covariant derivative. But having derived the properties of g mu, we then let go of this idea of the covariant derivative, and we tested the Lagrangian on its own to say, okay, we have our matter field psi and our gauge field g mu. We think we know how g mu ought to behave to give the thing local SU3 symmetry. And then we tested it, and it totally works. Under an arbitrary local SU3 transformation, our Lagrangian remains completely invariant, that is completely unaffected by the transformation. And it's important to point out the needle in the haystack nature of this problem. If you were to modify the definition of the gauge field in any way from what we have here, add on some term or whatever, it's not going to work. Because if you modified the gauge transformation rule from what we derived into something else, and repeat this exercise about checking if the Lagrangian is the same or different, what you'll find is that other thing you added is going to make it different. And so this transformation rule for g mu is what it has to be in order to give our Lagrangian local SU3 symmetry. And so from that perspective, we recognize that the gauge field blossoms naturally from local SU3 symmetry. So the transformation rule is not arbitrary, it's not some random thing. No, it's deeply and inexorably connected to the nature of local SU3 symmetry. Okay, so we found that the interaction term in our Lagrangian is negative g psi bar gamma mu g mu psi. But, what even is that? What does that mean? Well, for starters, if you look at the spacetime index mu, because it's repeated, this interaction term is actually a sum over each value of mu. So we have the same expression for 0, 1, 2, and 3. That is the time-like part and the three space-like parts of this interaction term. Oh, by the way, you may have noticed, here I'm writing it gamma mu g mu, whereas previously I wrote it as g mu gamma mu. Now, as we'll see in a moment, in this context, the gamma matrices and our gauge field commute. And so the order of the gamma matrices and the gauge field actually doesn't matter in this context. I probably should have kept it consistent for aesthetic reasons, but logically it doesn't make a difference. Now, the exact nature of this interaction term is a little complicated, and so we're going to explore it in more depth in part 5 of this video series when we get into the QCD Lagrangian. But for now, I just want to bring up a few parallels between the interaction term for electromagnetism and the interaction term for the strong force. So for electromagnetism, we found that our interaction term is given by negative q psi bar gamma mu a mu psi, where q is the electric charge, psi is the matter field, a Dirac bispinner, psi bar is its Dirac adjoint, gamma mu are the Dirac matrices, and a mu is the gauge field of electromagnetism, that is, the photon field. Now this term is a sum over the spacetime index mu, and so it's actually 4 terms in one. The term corresponding to mu equals 0, that is the time-like part of this expression, is the energy that pertains to charged matter in the presence of a voltage, that is the scalar potential, A0. Now for the space-like indices, mu being 1, 2, and 3, this expression encodes the energy that pertains to charged currents in a magnetic vector potential, because the magnetic vector potential is the space-like part of A mu. But if we look at it from a purely relativistic perspective, then we can interpret the interaction term as the energy due to a charged 4 current in the 4 potential. So the forecurrent J mu is defined as Q psi bar gamma mu psi, and the way that the forecurrent interacts with the forepotential, as given by our expression for the interaction term in the Lagrangian, you can see that it's actually just the minimal coupling that you could possibly have between our forecurrent J mu and the photon field A mu. So in electromagnetism, the interaction term in the Lagrangian is really nothing more than a charged forecurrent interacting directly with a forepotential. Now then, for the strong force, we can write the interaction term as negative g psi bar gamma mu g mu psi. And if you compare it to the interaction term from electromagnetism, you notice it's basically identical. In both cases, we have a real valued coupling constant. We also have a matter field and its Dirac adjoint. We have the gamma matrices, which pertain to the spin 1/2 nature of our particles. And we have a gauge field. And the only thing that's really fundamentally different is that we've upgraded our matter field to a color triplet field. And likewise, our gauge field has components that live in SU3, because, as mentioned earlier, quantum chromodynamics blossoms from the magic bean of local SU3 symmetry. And that's something we'll see over and over again, which is that the strong force is so incredibly identical to electromagnetism, but with just the minimal difference being it's SU3 instead of U1, and a different strength of the coupling constant. But there are profound structural similarities between electromagnetism and the strong force. So then on the basis of those similarities, it becomes very tempting and actually kind of accurate to think about G mu as being comprised of color voltage and a color magnetic vector potential, right? By analogy with electromagnetism, perhaps we would think that G0 is something like a voltage, but with more degrees of freedom, because our SU3 transformation has more degrees of freedom that we can use to mess up our matter field. But nonetheless, the time-like part of the gauge field, which transforms in accordance with the time derivative of our transformation, should behave kind of like voltage, right? But a kind of voltage that's sensitive to quark color. Well, sort of. Not really, but sort of. And likewise, for the spatial part of G mu, that's G1, G2, G3, we might think of this as kind of like a color analog of the magnetic vector potential. And there is some truth to that, in that the space-like parts of our gauge field are indeed sensitive to the spatial gradients in our gauge transformation in our matter field. But the problem is that this notion of a potential, whether you're talking a scalar potential or a vector potential, in a non-abelian gauge theory, it doesn't quite work. And the reason that it doesn't work, as we'll see in the next video, is that in a non-abelian gauge theory, our field strength tensor actually depends on our gauge field via the commutator in a way that makes the gauge field sort of more alive and more energetic than what we would expect in an abelian gauge theory. And so even though structurally in some ways you can think of the components of the gauge field as being sort of like color voltage and sort of like color magnetic vector potential, unfortunately it's not quite so simple, and the notion of the gauge field working as that kind of a potential doesn't quite fit. And that's why we're going to save a more in-depth exploration of this for part 5. Because to really understand this, we have to derive the field strength tensor, and then we have to put together the whole Lagrangian of quantum chromodynamics in order to examine this in a deeper context. You know what? Now would be a good time to take a moment to explain where the U-dagger sandwich comes from, our adjoint transformation, in the gauge transformation rule of G mu. Well, as we know, our matter field psi interacts with our gauge field G mu in a way whose energy is encoded in the interaction term in our Lagrangian, negative g psi bar gamma mu g mu psi. Now, when we apply a local SU3 transformation to hop from one gauge to another, we're going to be able to change how scrunchy and floppy psi is by messing around SU3 style with psi at different amounts in space and time. So psi bar becomes u psi, and as we've seen, g mu becomes g mu prime equals u g mu u dagger, plus a derivative term which cleans up the mess pertaining to the gradients of our transformation. Now, when we do a transformation like this, the derivatives of psi are going to change. And that's going to change the Dirac Lagrangian, the part of our Lagrangian that has to do purely with psi, based on its derivatives and mass. But when the Dirac Lagrangian changes, our interaction Lagrangian is going to change in an equal and opposite way, so that the sum of the Dirac Lagrangian and the interaction term remains constant. And that right there is the essence of local SU3 symmetry. But now if you think about a global SU3 transformation, that is, a transformation where U is a constant SU3 matrix everywhere throughout spacetime, well then there are no gradients, and so our gauge transformation rule reduces simply to this adjoint transformation, this U dagger sandwich. And to understand why that's how it is, all you have to do is think about the fact that under a global SU3 transformation, we should expect not only the entire Lagrangian to remain the same, but specifically we should also expect the interaction term itself to remain the same. Because a global SU3 transformation is effectively just a redefinition or a reorientation of our coordinate system in color space. But there's none of this changing the scrunchiness or the floppiness of psi, and so the interaction term isn't going to adjust itself to clean up that mess. But instead, however strongly the matter field and the gauge field are interacting, that should remain precisely constant. Just because we're reorienting our definition of color space, that alone shouldn't be able to affect the interaction term in our Lagrangian. And that insight is all you need to completely understand where the U dagger sandwich comes from. Because if we expect that the interaction term in our Lagrangian should be equal to the transformed interaction term under a global SU3 transformation, and we write that out, well, what happens is psi becomes U psi, psi bar becomes psi bar U dagger, and G mu becomes U G mu U dagger. But now if you look at that equation, and if you remember that U is an SU3 matrix, and therefore U dagger U equals I, well, you see that to the left and to the right of G mu, we have a couple of U daggers that annihilate each other and go away. So when you see the U dagger sandwich, think of that as something that clicks into the psi bar U dagger on the left and the U psi on the right. You see what I mean? Now, one of the themes that we've run into is that the strong force is basically just electromagnetism, but with the U1 replaced with SU3. And if you repeat the same exact reasoning, but with U equals e to the I theta being a U1 element, and U dagger equals e to the negative I theta, you'll see that secretly, even in electromagnetism, we have a U dagger sandwich, but it's just that in that case, all the scalars commute, and then you end up with e to the I theta canceling out e to the negative I theta. And so that's why secretly the U dagger sandwich is there for electromagnetism, but it just equals 1. And so we don't even realize that it's there. But secretly it is. And likewise, in electromagnetism, you also have the psi bar U dagger and the U psi, but because everything commutes, those cancel themselves out, and so both pairs of the U daggers that we're dealing with here, both just naturally vanish on their own. And so we don't really have to think about the adjoint transformation when we're dealing with electromagnetism, because it's an abelian group where everything commutes. Now, let's go ahead and examine the interaction term from a purely algebraic perspective. Like, let's say we're putting on our mathematician hats, and we're not even thinking about the physics necessarily. We just want to know what kind of an object is this negative g psi bar gamma mu g mu psi. Well, when you think about it, you notice one of the things that actually makes this kind of a tricky expression to parse is that the gamma matrices pertain to the spin indices of our particles, whereas our gauge field pertains to the color indices. And so how do we have this gamma matrix times this gauge field, and what kind of a psi are they acting on anyway? So in order to resolve this confusion, we're about to write things out in a level of gory detail that is absolutely overwhelming and terrible to look at. But trust me, this will actually give you a better understanding of what's going on here. Okay, so for starters, we're going to go ahead and write out our color triplet field psi explicitly in terms of all of its complex components. So as we talked about in part 1, quarks are spin 1/2 particles. Their wave functions are therefore Dirac bispinors with 4 complex components at each point in spacetime. And then we introduced this notion of quark color, and that changes the situation from a regular old spin 1/2 particle to this kind of 3-layer color situation that we're contending with as we develop quantum chromodynamics. And very often, in fact almost always, you can think about psi purely in terms of being a complex triplet, and just keep in mind that behind the scenes, each of those 3 complex numbers, red, green, and blue, actually corresponds to a Dirac bispinner, but you can often just put those spinorial details out of your imagination, carrying them through algebraically but not necessarily having to visualize them. Well, in any case, what I've written here is our wave function psi, written out in its full 12 complex component form. Now notice I've transposed this, the reason being that psi is actually a column, but in order to fit it on the screen, I went ahead and wrote it as a row that's being transposed. But that's just an aesthetic thing, okay? So in your mind, imagine psi as a column of 12 complex numbers. Now then, psi bar is the Dirac adjoint of psi, and that's going to be psi dagger times gamma 0, which all that really means is we're going to flip psi on its side, take the complex conjugate of everything, and then on the 3rd and 4th spinor components, we're going to slap on a minus sign. That's what the gamma 0 does. Now then, the gamma matrices are a set of 4x4 matrices, and to be totally generic, we can go ahead and write them out like so. Gamma mu is a matrix comprised of 16 numbers. Here we may as well index them gamma 1, gamma 1, and so on and so on. And all I mean by that is I'm representing the fact that each gamma mu is a 4x4 matrix, and we have 4 gamma matrices, 1 for each dimension of spacetime. Now we've talked about the gamma matrices in my video on deriving the Dirac equation, as well as in the electromagnetism video, so I'm not going to rederive them here in the interest of time. The main thing to know about the Dirac matrices is they're sort of like the square root of the Minkowski metric, and they're what allow us to take the square root of the relativistic dispersion relation, which is what enables us to derive the Dirac equation. Okay, but for what we're talking about today, we don't really have to go too deep into the nature of these gamma matrices. We can kind of just carry them through as constants, because we're mostly focused on what's going on with color, you know what I mean? And that brings us to the gauge field G mu. So at this point of our derivation of quantum chromodynamics, we don't know anything about G mu, other than that it appears to be, for now, a generic, complex 3x3 matrix. So we may as well write its components like so, G mu 1, G mu 1, and so on and so on. Now let's go ahead and color in the different elements of these matrices. The colors shown here have no meaning whatsoever. The only purpose of them is to give us a visual way of seeing the different components of each matrix. Now what we're about to look at is pretty disgusting, I'll be honest, okay? But we're going to write out the expression -g psi bar gamma mu g mu psi in full detail down to every last complex component, okay? So are you ready for this? Here we go. Ugh, what a gross mess this is. Looks like we spilled our fruity pebbles. Oh my gosh. But hear me out, okay? So the good news is, in practice, you never have to write this out. Don't worry, if you're studying QCD, it is not about writing out 12x12 matrices. This is unbearably tedious, and so you never have to see this matrix again. But the other good news is that by looking at this matrix for just a moment, there are 2 very profound and very memorable lessons that we can learn. And that's why I'm showing it, okay? I'm sorry to assault your eyes like this with this terrible mess, but just bear with me, okay? Alright, well, something that makes it a little easier to look at is if I put these lines here, you can see that we can break this matrix up into 9 different blocks. Now, the first lesson that we can learn by looking at this matrix is that the gamma matrices act on a different set of indices than our gauge field. See, because gamma mu pertains to the spinor indices of our wave function, whereas our gauge field G mu pertains purely to the color indices of our wave function and is completely insensitive to the spin indices. And that's actually very nice because it means that gamma mu and G mu, they don't trip over each other. They don't get all tangled up. Each one sort of minds its own business, okay? And the reason for this makes sense, right? Because quarks are spin 1/2 particles, their wave functions are Dirac bispinor fields, but when we're developing quantum chromodynamics and we introduce this notion of color, and our wave function goes from being this colorless Dirac bispinor field to being this sort of three-layer, three-color situation, the introduction of those colors doesn't change the fact that quarks are spin 1/2 particles. And so everything just kind of gets copied and pasted as far as the Dirac matrices are concerned. And if you look at it here, in each block of this big matrix, it's just our Dirac matrices copied and pasted 9 times. And think about what that means in this context. Well, because each block of this matrix is just identically the Dirac matrix, when this multiplies into our 12-component wave function, the Dirac matrices are going to act within each color, but there's nothing different from one color to another as far as the Dirac matrices are concerned. The Dirac matrices are completely and entirely insensitive to color. And likewise, if you think about color, you think about how we brought in this 3-layer situation into our wave function, and then we're messing it up with a local SU3 transformation, which is like reorienting ourselves in color space from one point to another in spacetime. Well, that has nothing to do with the spin 1/2 nature of a quark. And so our gauge field G mu, which comes in to clean up the mess that we're creating in color space, it's only concerned with color and adjusting for what we mean by how color changes from one point in spacetime to another. But G mu is going to be totally insensitive to the spinor degrees of freedom within each color. And so that's why we say that gamma mu acts on the spin indices, and G mu acts on the color indices. And so in a certain sense, in this context, each can be viewed as sort of like a constant from the other's point of view. They sort of operate on different spaces. So that's the first profound lesson we can get by looking at this terribly messy matrix. The second lesson is that we can see that the interaction term is going to be a scalar-valued thing. The reason being, you look at the matrix here, and it's a 12 by 12 matrix comprised of complex numbers. Well, when that multiplies our column of 12 complex numbers, we're going to end up with a transformed column of complex numbers. And then, when that transformed column of complex numbers is left multiplied by our row of complex numbers, you have a row times a column, and that's going to end up giving you a scalar. So structurally, just by examining the dimensionality of the situation, we know that for sure our interaction term is at least going to be a complex-valued thing. And that's assuming that the spacetime components of our gauge field, G mu, are comprised of purely generic 3x3 complex matrices. Right? We haven't yet put any constraint on the kind of matrix that G mu can be. But the thing about a Lagrangian is that it can't be complex-valued. It has to be real-valued. And so it is good that dimensionally we know that it has to at least be complex-valued, as opposed to being like a vector or a matrix. But we do have to insist that this Lagrangian term should be real-valued, and so we have to restrict it in the complex plane to being purely on the real number line. Only then is our Lagrangian physically meaningful, because it encodes energy, right? And energy has to be real. And so the question comes up, how is that going to constrain our matrix G mu? So that's a great question, because that's going to lead us into a very meaningful and very important constraint on the kind of thing that G mu can be. Okay, now if you don't mind, this terrible mess of a 12 by 12 matrix, let's not worry about that anymore, okay? What we'll do instead is we'll think about it like this. So here we've gone ahead and written our wave function psi as a complex triplet. Behind the scenes, of course, we always remember that each component is in fact a Dirac bispinor, and that our gamma matrices act on their spin indices. But put that to the back of your mind, okay? Put that in the subconscious. We'll carry it through algebraically, but in your imagination, let's think only in terms of the color degree of freedom and the color triplet field and the way our gauge field acts on that color triplet field. Okay, so now let's answer the question of when we require our interaction term to be real valued, what constraint does that impose on G mu? So the key insight is that in order to insist that our interaction term is real, all we have to do is say L dagger equals L. Because in all the possible complex numbers, the set of numbers that satisfy that equation is precisely the set of real numbers. All right, so when we write out the interaction term in our Lagrangian, we have negative g psi bar gamma mu g mu psi. In that equation, our coupling constant g, as well as the gamma matrices, are both constant, while our wave function and its Dirac adjoint are totally generic. They can be whatever they can be, and so the constraint that L dagger equals L is necessarily only a constraint on what our gauge field can be. Because we can't change g or gamma mu even if we tried, and we have no control over psi. Okay, now to see exactly what kind of constraint this puts on g mu, we're going to have to use a couple of identities. The first one is that psi bar, the Dirac adjoint of psi, is equal to psi dagger times gamma 0. So that's the definition of the Dirac adjoint. Now from that definition, I also want to point out that if you take the transpose conjugate of the Dirac adjoint, based on that definition, you end up getting gamma 0 times psi. Because gamma 0 is equal to its own transpose conjugate, and psi dagger dagger equals psi, and you switch the order of things around when you take the transpose conjugate. And the other identity that we'll use is that the transpose conjugate of a gamma matrix, gamma mu, equals gamma 0, gamma mu, gamma 0. And that's one of those identities that pertains to the Dirac matrices. You can test it for yourself if you want. Pick any of the 4 Dirac matrices, or do all of them if you have a lot of free time, and you can confirm that this identity is indeed true, but in the interest of time, we'll just take this as a given. Okay, so we're requiring that L dagger equals L in order to ensure that L is a real number. So if we evaluate the transpose conjugate of our interaction term, a negative g is a real scalar, so that simply comes down. For everything else, we can go ahead and switch the order around and take the transpose conjugate. The psi bar on the left becomes a psi bar dagger on the right. Gamma mu becomes gamma mu dagger. G mu becomes G mu dagger. And psi becomes psi dagger. Now here, I will point out that because G mu and gamma mu commute, because they act on different indices, the gamma matrices act on the spin indices, G mu acts on the color indices, the order in which we multiply those two things actually doesn't matter. So the green and the yellow terms here, we could have written them gamma mu dagger, G mu dagger. Either way is totally fine. Alright, now to simplify this expression, the first thing we want to do is use our identity that psi bar dagger equals gamma 0 psi, and then also we'll go ahead and use our identity that gamma mu dagger equals gamma 0 gamma mu gamma 0. And so we can write the equation out like so: negative g psi dagger g mu dagger gamma 0 gamma mu gamma 0 gamma 0 psi. These equations are fun to say. And now we're going to notice, wait a minute, gamma 0 gamma 0, that's the identity matrix. And so that's just multiplying by 1, so those terms go away. And then we can write the equation in a more simple form, like so. Now next, what we can do is we can notice that there is a psi dagger gamma 0 in this equation. And we know from the definition of the Dirac adjoint that psi dagger gamma 0 is equal to psi bar, the Dirac adjoint of psi. Now here, in order to use this identity, we have to scoot our gamma 0 over to the left side of G mu dagger. And so we have to ask ourselves, is that an okay move? That is, does gamma 0 commute with G mu dagger? Well, remember the fruity pebbles. Yes, these things commute, because gamma 0 acts on the spin indices, and G mu dagger, which is based on G mu, acts on the color indices. So the order of multiplication doesn't matter, therefore we can bring gamma 0 on over to the left. We can unify it with psi dagger, and what we end up with is a psi bar. And now, would you look at that? The expression we found for L dagger is negative g psi bar gamma mu g mu dagger psi. It's like, whoa, that is so similar to the original interaction term before we took the transpose conjugate. The only thing that's different is that in our interaction term we have g mu, and in our transpose conjugate of the interaction term, we have the transpose conjugate of g mu. But everything else is exactly the same. And so therefore, L dagger equals L if and only if G mu dagger equals G mu. Wow, what a neat result. Isn't that cool? But now let's phrase it in a more powerful way. Because remember, this thing about L dagger equals L, why does that matter? Well, because that's the definition of L as a real number. And what is G mu dagger equals G mu? Well, that's the definition of G mu as a Hermitian matrix. And so we come to a most profound conclusion, that our interaction term is going to be real valued if and only if G mu is a Hermitian matrix. Wow, isn't that cool? Now, another way to say that is that G mu has to live in the Lie algebra of U3, or perhaps a subalgebra thereof, like for example SU3, the Lie algebra of SU3. Now, in a moment, we'll get into why it's actually SU3, but remember, SU3 is the traceless subspace of the Lie algebra of U3. So for now, what we've done here is that by insisting that our interaction term in the Lagrangian is real valued, we have restricted the spacetime components of G mu, whereas before we thought that they could be any generic 3x3 matrix. Now we know that actually they are confined to at most the 9-dimensional space of Hermitian 3x3 matrices. Because if G mu were to poke out of that space, then our interaction term in the Lagrangian would be complex valued, that is to say, physically absurd. And so we're starting to box in the kind of thing that G mu has to be. Okay, so now that we know that the spacetime components of our gauge field G mu have to be Hermitian matrices in order to ensure that the interaction term in our Lagrangian is real valued, there's a potential problem that might arise, and so we have to make sure that it doesn't arise. So the thing is, if the components of our gauge field are Hermitian, are we sure that under any local SU3 transformation, when G mu becomes G mu prime in the new gauge, is it going to remain Hermitian? Or is the gauge transformation rule going to convert the Hermitian components of G mu into non-Hermitian matrices? Because if that happened, if the components of G mu became non-Hermitian under a gauge transformation, then in that gauge, the interaction term in the Lagrangian would not be real valued, and that would render our whole model tragically incoherent. So as a consistency check on the ideas that we've been talking about, we need to ensure that if we start off with the Hermitian gauge field, with G mu equals G mu dagger, then in any other gauge, the components of the transformed gauge field are also Hermitian. So G mu prime equals G mu prime dagger for any G mu prime that we can get to from a local SU3 transformation. Well, fortunately, we can demonstrate that this is the case, and it's not even that long of a calculation. So basically what we want to do is write out G mu prime, given by our gauge transformation rule, so that's going to be an adjoint transformation acting on G mu, plus that derivative term that cleans up the mess that we'd otherwise be creating in psi. And then to see if it's Hermitian or not, all we have to do is take the transpose conjugate of the gauge field in the new gauge, and see if the gauge field in the new gauge equals its own transpose conjugate. So if this equation is true, then yes, the components of the gauge field will remain Hermitian in every gauge. Okay, so all we have to do is evaluate the transpose conjugate of the right-hand side of this equation. Focusing first on u G mu u dagger, we can go ahead and evaluate the transpose conjugate, and when we do that, we're going to switch the order of the matrices in that product. So we end up with u dagger dagger times G mu dagger times u dagger. Now on the left side, the u dagger dagger is actually just u, because if you take the transpose conjugate of the transpose conjugate of a thing, you just end up with the thing itself. And so for that left term, the adjoint transformation term, when we take its transpose conjugate, what we end up getting is the transpose conjugate of the gauge field in a u dagger sandwich. Now for the derivative term, if we take the scalar I over g, take the transpose conjugate of that, and you end up with the scalar negative I over g. Now take the transpose conjugate of partial mu u times u dagger, and what you end up with is the transpose conjugate of u dagger, so that's u, times the transpose conjugate of the derivative partial mu u. Now if you look at the two sides of this equation, they look kind of similar, but it's not totally obvious that the left-hand side of the equation is exactly equal to the right-hand side. But remember, U is a matrix in SU3. So if you were to add this purple term and this pink term, and do an inverse product rule, you see that partial mu of U times U dagger plus U times partial mu U dagger equals partial mu of the product of U and U dagger. right? Because if you read it from right to left, that's the product rule. But then U dagger, because U is an SU3 matrix, is simply the identity matrix I. And so you end up with the derivative of the identity matrix, which is 0. So if the sum of that purple term and that pink term is always 0 for an SU3 matrix U, then it follows that the purple term and the pink term are the same, except for a minus sign. But you see on the right side of the equation, you have a minus sign on the I over G. So that minus sign cancels out with the other minus sign. And at the end of the day, we can delete both the purple and the pink terms from the equation. That leaves us with the equation UG mu U dagger equals UG mu dagger U dagger. So is that equation true? Well, yes, because we took as a starting point the fact that our gauge field in the original gauge is Hermitian. So G mu equals G mu dagger. And if G mu equals G mu dagger, then UG mu U dagger equals UG mu dagger U dagger. That's kind of a tongue twister. But I said it. On the third try, but you don't know that. So the point is, it's not a problem. If you start off with a gauge field whose spacetime components are Hermitian matrices, then under a transformation given by our gauge transformation rule, the gauge field in the new gauge, G mu prime, will also be Hermitian. So in that regard, we find that our model is internally logically consistent. Okay, so the next thing we're going to do is we're going to show that if G mu has any trace, we can go ahead and shave that off without any loss of physical generality. What I mean by that is we've just seen that if we want the interaction term in our Lagrangian to be real valued, then the components of G mu must be in the Lie algebra of U3 because they have to be Hermitian matrices, and the Lie algebra of U3 is precisely the space of all Hermitian 3x3 matrices. Now, because of part 2 of this video series, we're experts on group theory, and we know that the Lie algebra of U3 is a 9-dimensional space. And so our gauge field G mu has, at most, 9 degrees of freedom at each point in spacetime. If you tried to give G mu another degree of freedom, say 10 or 11 or 12, well, you'd have to poke out of the space of Hermitian matrices. And that's not allowed because then you'd end up with a complex valued interaction term in the Lagrangian, and we can't have that. I mean, come on. But because our transformation matrix field U of X lives in SU3, that means we have 8 degrees of freedom in how we can mess up our color triplet wave function psi at each point in spacetime. So that's 8 degrees of freedom, not 9 degrees of freedom, 8. And so therefore, we might suspect that actually, rather than having G mu in the Lie algebra of U3, perhaps G mu should live only in SU3, the Lie algebra of SU3, which is the traceless subgroup of U3. And so if you imagine SU3 as an 8-dimensional subgroup within the Lie algebra of U3, all you have to do is compress that 9-dimensional space down into 8 dimensions along the direction of the identity matrix. So you're basically just taking out any ability for the matrix to have any trace to it whatsoever. And the reason we associate the identity matrix with the trace is that the trace of a matrix is the sum of its diagonal elements. And when we think back to what we saw earlier about the generators of the Lie algebra of U3 and SU3, you see that the identity matrix is the only one that contains any trace. Now, another way to look at it is we're building our model of quantum chromodynamics on the basis of SU3, not U3. Had we instead started with U3 color symmetry, we would end up at a very similar model, but it would contain an extra U1-like degree of freedom, an extra global phase degree of freedom in our transformation matrix field U of X. And if we derive QCD starting with U3 color symmetry, then our gauge field would have to have 9 degrees of freedom, and it would have to live in the Lie algebra of U3, and we would end up with a 9th gluon field, which in many ways is sort of like the photon field, but in many important ways is different. But never mind all that. The only point I want to emphasize here is that starting with SU3, we don't have that global phase degree of freedom, so we don't have the 9th gluon field. And so therefore, the constraint that the components of our gauge field G mu have to be Hermitian matrices is kind of loose in that we should still expect our gauge field to contain an irrelevant, traceful component which has no effect whatsoever on the physics of the situation. And specifically, the way we can write that is that the components of our gauge field G mu can be thought of as their traceless component plus alpha times the identity matrix, where alpha is a real number. So this blue term here, G mu traceless, think of that as a component of the gauge field that lives in SU3 and has this 8-dimensional habitat that it resides within. And then that orange term plus alpha I is some distance alpha along the direction of the identity matrix that is along the traceful generator of the Lie algebra of U3. So what we're about to see is that this term, alpha I, does not participate in the interaction term in the Lagrangian, and is therefore not physically real. And so therefore we can set alpha equal to 0 without any loss of physical generality, and having done that, we'll then arrive at the beautiful conclusion that the components of our gauge field G mu live in SU3. Okay, so to demonstrate that alpha I, a hypothetical traceful part of G mu, would be unphysical, all we have to do is write the components of our gauge field like so, like we saw earlier, and now just hop into a different gauge and show that the alpha I term doesn't change. So we know that when we hop into a new gauge, G mu is going to become G mu prime. So G mu goes in the U dagger sandwich, and then we add on the derivative term. Well, substituting in G mu as G mu traceless plus alpha I, we find that alpha I becomes one of the ingredients in our U dagger sandwich. We have the hamburger patty of G mu traceless, and we have the lettuce of alpha I. Okay, so I went a little too far with that metaphor, but you know what I mean. So the question becomes, what is the deal with this alpha I term in the U dagger sandwich? Well, if you isolate that term, you end up with U, alpha I, U dagger, but alpha is a scalar, so that commutes with everything, and I is the identity matrix, which also commutes with everything. So we can write that expression as alpha I U dagger. Well, U is an SU3 matrix, so U dagger equals I, so those matrices annihilate each other, and then you end up with alpha I. And that teaches us that alpha I in a U dagger sandwich is completely unaffected. And so therefore, we can take that alpha I term and move it all the way out of the gauge transformation rule for G mu, and we can write the equation above as simply G mu prime equals the G mu prime of the traceless part of the gauge field plus alpha I, and the alpha I term doesn't change from one gauge to another. Now, why does that mean that the alpha I part of G mu can't have any physical consequences? Well, it's because of this. Alpha I, as we've seen, is invariant under local SU3 transformations. It simply doesn't change at all. But our color triplet field psi is very much not invariant under local SU3 transformations, because that's what the whole thing about the transformation is. That's what the transformation transforms is psi. And so if you had any interaction involving alpha I and psi, then alpha I stays the same, psi changes, and so the product or whatever interaction there is between alpha I and psi would change from one gauge to another. Because a same times a different is a different. Because think about the fact that the gauge field G mu and psi dance together from one gauge to another. Psi becomes U psi, G mu becomes U G mu U dagger plus the derivative term, and it's a dance, and they flow and they fit together. Alpha I doesn't change at all, it doesn't dance, so it creates a tripping hazard for psi. And the only way we could even try to include it in our equations without it being physically absurd is if it completely decouples from the interaction term, and on that basis, we can set alpha equal to 0 without loss of generality, without a difference in the physical predictions of the model. And we know that because alpha I doesn't change from one gauge to another, if we set alpha equals 0, then alpha remains 0 in every gauge. And that means that the components of our gauge field G mu live in SU3, the Lie algebra of SU3. Alright, so now that we've proven that the spacetime components of our gauge field G mu live in SU3, let's apply our knowledge of group theory to write our gauge field as 8 real-valued 4-vector fields. These are the gluon fields. So what do we know? Well, we know that the space of all SU3 matrices has 8 dimensions, because SU3 is all the traceless Hermitian 3x3 complex matrices. So you'll start off with 18 dimensions, the Hermitian constraint cuts that in half to 9 dimensions, and then the traceless constraint takes out another dimension, so you're left with 8 dimensions. So with that reasoning in mind, we know that if we can find a basis set T1 ... T8 of traceless Hermitian 3x3 matrices that are all orthogonal, then naturally they're going to span SU3, and therefore we can write any SU3 matrix M as a linear combination of those generators TA with real coefficients. And that's the technical way of saying that there's an octopus that lives in SU3. So if M is in SU3, then we can write M equals MATA, where we're summing over A, and all of the MAs are real numbers. And one way to think about that is that the matrix M sort of casts 8 shadows onto the generators in SU3. Although personally, I prefer the octopus metaphor. MA is just how far you have to go along the direction of the 8th tentacle in order to get to the matrix M. So then, if we're looking for a set of 8 traceless Hermitian 3x3 matrices that are all orthogonal, the famous Gell-Mann matrices, which are called lambda, have precisely the desired properties that we're looking for. But conventionally, it's common to go ahead and slap a normalization factor of 1/2 onto those matrices. So we'll define our generators TA as lambda A over 2. And that factor of 1/2 doesn't really matter, but it'll save us from having to deal with factors of 2 later on. So then if we have our gauge field G mu, whose 4 spacetime components live in SU3, we can break that up into 8 real-valued 4-vector fields, call them G mu A, where A is the index that corresponds to the generators of SU3, and these are the famous gluon fields. So if G mu lives in SU3, then we can write that as G mu equals G mu A TA for real-valued G mu A. Now, as we'll see when we get into the field strength tensor and the Lagrangian of QCD, each gluon field is very much like the photon field A mu, except there are gluon-gluon interactions which really complicate the situation and, in practice, lead to radically different behavior for the gluons relative to photons. But there are also some very striking similarities there as well. And by the way, those gluon-gluon interactions are not arbitrary or optional. No, as we'll see, these come directly out of the nature of SU3 and SU3. And that's related to the fact that the topology of SU3 is not an 8 torus. You know what I mean? It's a more complicated thing. It's like a fiber bundle over the 5-sphere with SU2 fibers that are all topologically non-trivial. And all of that complexity and the non-commuting, non-abelian nature of SU3 is what's going to tangle up all of these gluon fields, as we'll see later on. Okay, let's take a moment to review our model so far. Well, we have our quark color triplet field psi, which we can think about as just being a complex triplet, bearing in mind that implicitly you have Dirac bispinners behind the scenes. And then we also have our gauge field G mu, which is a 4-vector field, very much like the photon field, but instead of having scalar-valued components, it's comprised of components that live in SU3, the Lie algebra of SU3. So our matter field psi and the gauge field G mu are going to dance together as we hop from one gauge to another. An SU3 gauge transformation is defined by a field of SU3 matrices U of x, which can vary arbitrarily in space and time, although it should be smooth, continuous, and differentiable. The matter field psi is transformed into psi prime simply by left multiplying by our transformation matrix U. And in response to that, the gauge field G mu undergoes an adjoint transformation, that is the U dagger sandwich, and then also picks up a term pertaining to the derivatives of the transformation to clean up the scrunchiness and the floppiness of the mess that arises from the way the matrix field varies in space and time. Now, if we take just these two ingredients, we can construct a Lagrangian, which is the Dirac Lagrangian plus an interaction term, which, as we've demonstrated, is gauge invariant under local SU3 transformations. And so this model genuinely does have local SU3 symmetry. And notice here that we don't have to bake into our model this notion of the gauge covariant derivative. d mu is a useful tool, but it's not something we have to take as fundamental. It's more of just like a practical way of looking at things. Okay, so it seems like we're developing a pretty powerful model here. And I think you'll agree that this is the most elegant way to equip our Lagrangian with local SU3 symmetry. There's no simpler way to do it. Our gauge field is the minimally complicated thing that can ensure that our Lagrangian has local SU3 symmetry. And so you might think, great, we're done. We've done it. We've given our Lagrangian local SU3 symmetry, and so therefore, problem solved. However, problem not solved, because the model shown here is physically nonsensical. Now, to be fair, it is mathematically coherent, but physically it's incomplete. The reason being, if you look at our Lagrangian, we have the Dirac term, which pertains to the kinetic energy and the mass energy of our matter field, and we have the interaction term, which pertains to the way in which the matter field and the gauge field interact, but we don't have any term that gives our gauge field a life of its own. And so what are we saying here? We're saying that there exists a field, but it only exists insofar as it interacts with our matter field, and it has no life of its own? It can't contain any of its own energy? Well, that doesn't make sense. That's not good physics. We do need to summon this gauge field. We do need to bring it into existence, because it is the way to give our model local SU3 symmetry. But existence has consequences, and if you want to summon a gauge field, you have to summon it all the way. You have to unleash it as a dynamical entity and deal with the consequences, okay? I mean, that's just life. That's how it works, you know? Your gauge field has to be able to jiggle on its own throughout the universe, and you have to be able to quantify how much energy is in that jiggling. Only then have you responsibly summoned the gauge field in a way that makes good physical sense. So how do we give our gauge field a life of its own? Well, if you think back to electromagnetism, there we found a gauge field A mu, a four-vector field whose components were real valued, that is, they lived in the Lie algebra of U1. And we derived the rule for how A mu has to change from one gauge to another. But then again, we had exactly the same problem of, okay, this is great. This gauge field can give us a way of giving our Lagrangian local U1 symmetry. But our photon field A mu needs to have a life of its own in order for it to be real, like for real, actually real, not just a mathematical thing. And so we thought about it for a while, and we realized that the only kind of a thing we could make out of A mu and or its derivatives is this expression, partial mu A nu minus partial mu A mu, because that expression is uniquely unaffected by the transformation of A mu becoming A mu prime. So therefore, in any gauge, partial mu A nu minus partial mu A mu is going to be the same. And because it remains the same in every gauge, we can have real, actual for real energy corresponding to this mathematical object, which we call F mu nu, the field strength tensor. And when you examine what are all the possible options for mu and nu, at first you think, okay, well, there's 4 space-time dimensions, and so you got 4 options for mu and 4 options for nu, so therefore you have 16 different ways of doing this, and you can write them in a matrix like so. But then you notice that all the diagonal terms, where mu equals nu, those are all going to cancel out to 0. Because you'll just have a thing minus itself, and a thing minus itself is 0. So actually, the field strength tensor does not contain 16 degrees of freedom. It only contains 12 degrees of freedom. But then you consider the fact that, wait a minute, you only need to look at one half of this matrix, because if you switch the mu and the nu, that is, if you compare a term of the matrix with its mirror image, they're the same up to a minus sign. Because if you look at the definition of F mu nu, switch the indices around, you just pick up a minus sign. So actually, there are not 12 degrees of freedom in our field strength tensor, but in fact, we have only 6. And these we whimsically call the 6 ways. Now, I know this term, the 6 ways, is not like standard or professional, but the reason I emphasize it so much is that I want to anchor this concept in your mind that the electric and magnetic fields are actually two sides of the same coin. So the electric field is a 3-vector, it has 3 real degrees of freedom. The magnetic field is a 3-dimensional pseudovector with 3 real degrees of freedom. But you reach a new level of electromagnetic understanding when you see that in reality, these are just the 6 ways. And you can derive Maxwell's equations from that fact. Well, anyway, once we have our field strength tensor, then we can think about what are the real scalar quantities that we can make out of our field strength tensor. And as we saw in the electromagnetism video, basically the answer is F mu nu, F mu nu. There's a couple of nuances and caveats there that we talked about in the other video. I won't go over those again today in the interest of time. This is a Lorentz invariant quantity, so it'll be the same real number for all inertial observers, and at the same time, this quantity is totally unaffected by a local U1 transformation, because as you hop from one gauge to another, F mu nu doesn't change, and so therefore, F mu nu doesn't change. Okay, well that was a super fast summary of something that we spent a lot of time going into detail on in the electromagnetism video, so if you want more detail on that, you can check out that video. But the reason I bring it up is that in the next part of this video series, we're going to be doing a very similar thing for the strong force that we did for electromagnetism. Because again, we know that we have this gauge field, and we know that the spacetime components of the gauge field live in the Lie algebra of the symmetry group, and we also know how the gauge field has to transform from one gauge to another. And just a reminder, this transformation rule for G mu is actually exactly the same as the transformation rule for A mu if you convert G mu into a real valued 4-vector field and you set U equals e to the I theta. So we see that there's a deep structural unity between electromagnetism and the strong force. So naturally then, our intuition leads us into asking the question of whether we can find some rank 2 tensor F mu nu, which is unbothered by our gauge field undergoing a transformation from one gauge to another. Now, as we'll see, there are some nuances about what we mean by unbothered, because in the case of electromagnetism, we wanted our F mu nu to remain exactly the same from one gauge to another. But having dealt now with the non-abelian gauge theory of QCD, we might think instead that we want our F mu nu to simply undergo an adjoint transformation, that is, to go into a UU dagger sandwich, so that as we hop into a new gauge, the field strength tensor is going to properly reorient itself in color space, but otherwise remain totally unaffected. But we'll talk more about that in the next video. For now, I just want to give you some foreshadowing about what's to come. So, spoiler alert, we are going to be able to find a rank 2 field strength tensor, F mu nu, and much like the 6 ways of electromagnetism, we're going to find there's the 6 ways of the strong force. And the fields that these 6 ways correspond to, if you want to break it up in the language of electricity and magnetism, you can think of them as color electric and color magnetic fields. But there's a plot twist. You see, in electromagnetism, the components of our field strength tensor, F mu nu, are real valued. They live in the Lie algebra of U1. But in quantum chromodynamics, the components of our field strength tensor, F mu nu, live in SU3, the Lie algebra of SU3. And what do you know about SU3 matrices? Well, there's an octopus that lives in SU3. And according to that octopus, every SU3 matrix can be thought of as 8 real numbers. So in quantum chromodynamics, we're going to end up with 8 real-valued field strength tensors. And that doesn't just come out of nowhere. That comes out of local SU3 symmetry. That's part of the magnificent blossoming of the magic bean of SU3. Now, each of those real-valued field strength tensors we can label as F mu nu A, where A is the index corresponding to the generators of SU3, and then when we construct a Lagrangian term pertaining to those field strength tensors, that is, a Lagrangian term that captures the independent life of the gluon fields, we're going to find that it's the same as the photon field's Lagrangian, but with the sum over all of those 8 field strength tensors. So, I mean, it's a remarkable similarity between electromagnetism and the strong force. Now, I should point out that there is a difference between the F mu nu of electromagnetism and the F mu nu of the strong force, which is that the F mu nu of the strong force contains a commutator term which is going to tangle up all our gluon fields together and lead to a Lagrangian which gives us gluon-gluon interactions. But we'll save that for the next video. I think for today we've learned a lot, we've made a lot of great progress, we derived a gauge field, we've seen that its components live in SU3, so we're doing great. So thank you for joining me on this wonderful adventure into quantum chromodynamics, and I'll see you next time. I want to say thank you to everyone who's been supporting the channel on Patreon. Your support really means a lot, and it's been so gratifying to see so many new people signing up lately. Welcome to the club. And I want to give a special thank you to Jack Serino, Andy Jones, and Edward, who are supporting the channel at an incredibly generous amount. You know, at the moment I'm actually between jobs, and I'm kind of seeing, is there a possibility to do YouTube either full-time or even just as like a part-time job that I can supplement with other part-time work as a way of kind of making ends meet? And it's looking like the answer is actually maybe. I mean, I don't want to get my hopes up too soon, but seeing your guys' level of support, it really means a lot. And it's incredibly gratifying and motivating. All right, well, I gotta go work on part 4. Thank you for watching this video, and I'll see you in the next one.